Good evening, everyone. Welcome to today's problem-solving section, course Digital Design with Verilog, week 10. So, in today's class, we will be seeing about the optimizations. So, let's briefly describing the some slides. So, we have seen that any sequential system can be represented using the state diagram. And next, so shift registers. So, this is the uh, state diagram for the shift register. So every state we need to represent three. We need 3 bits to represent because we have 3 flip flop. And so let's just see one example. Say the shift register from this state. If the input is 1, then the value will be this one. If the input is 0, then it will be this right as the next state diagram. So the present state, next state based on the input is equal to 0 or input is equal to 1. So the present state is this. The shift register, if we have 0 as the input, the next state will be this. And if 1 is this input, then this will be there. Similarly, if we consider, say, this state, or say I will take 1. Now, if you want to shift 0, then it will be all 0. If it is 1, then it will be 1, 0, 0. So in this example, you can see when the input is 1, it goes to 1, 0, 0. Input is 0, it remains in the state. And from 1, it goes to 0 if the input is 0. And it goes to 4 if the input is 1. So this way you can represent the shift register using the state diagram. Next, the FSM. Okay, this is the FSM. So FSM for the counter. So the present state and next state table. If you see the counter is 3-bit counter with upcounting. And so we observe that, say we are in the state 0, 0, 0. The next state it should go is 0, 0, 1. And from this, it should go to the next state, which is 0, 1, 0. And to the next state, which is 0, 1, 1. And from this, it is going to 4 to 5, 6, 7. And from 7, back to 0. So and this is the FSM for the counter. Next, if we have a 5-state counter, like counter which counts only the 5 sequences. Sequences are as given below. Take for example, if the sequences are 0, 1, 2, 3, 5, 6, and 0. So these are the 5 sequences. So from if it is going to state 1, the next state is don't care, like it is unknown. And from 4, it is again okay, and from 7, it is okay. So these 3 states are invalid state. And from 1 to, like from 0 to 2, 2 to 3, 3 to 5, 5 to 6, and again to 3. This is the side state counter. So is this design robust? So in our design, for example, by any chance if the circuit goes to a state, say if the circuit is in 1 state, then we don't know to which state it will come because these are the valid state. These are the valid state. If it is in this or 1, and what else is it? Oh. So these states are like invalid states. So what if the counter is in the state? So does our counter stuck if the counter gets stuck in this invalid state? So we should have some mechanism to bring from this invalid state to a valid state. Okay. So for that, we need to have some modification in the state diagram. Like for example, if it is in state 1, it should come to 2. If it is in 7, to 4 to 6. So that if it is getting stuck at this invalid state also, the circuit has the mechanism to come back to the valid state and start the counting again. So these are self starting counters. Like invalid state should always have a transition to a valid state so that we can assure the startup and bit error tolerance. So design your counter to be self-starting. So for that, you should consider all the states, the state diagram, and fill in the entire state transition table. But if we have the don't cares, we will have a minimum circuit. But if it is getting stuck in a particular state, then correction will be like difficult, either like performing a restart or something is needed, a reset is needed. So this may limit the ability to use this don't care for minimization. And we choose the startup transition that minimize the logic. So we want Hamming distance to minimum. So here Hamming distance is 3, 2, 2. So total Hamming distance is 7. But if we have like this, the total Hamming distance is only 3. So what is Hamming distance? This is the one port, another port. Here there is a big change. So what is the Hamming distance? The total Hamming distance is obtained for 1 plus 3, which is 3. 1 plus 1 plus 1 is 3. Okay. So now counter design based on FSM using JK flip-flop. So FSM implementation. In default, we use the D flip-flop for the simple to design. So this can like it can be designed with other flip-flops too. And what are the benefits that we have JK flip-flop? Then we have 2 inputs, dual inputs. Counters can be implemented using smaller combinational circuit, like if we have other flip-flops, and more inputs from the combinational circuit. So if we consider this as the finite FSM for the 2-bit counter, so it is counting 0, 1, 2, 3, it's up counting. And so this is the present state, next state table. So 0 to 1, 1 to 2, 2 to 3, 3 to 0. So we have a set of state registers and we need a combinational logic. So to give the next state and the state output. So uh, just a second. This things. One zero one zero. Yes. So we have got the equations. So we have a state register. Say, for example, we are using the D flip-flop person. So this output is obtained at the these are the state values, and we want to get this as the output n0 n1. So this table of form of the person, present state and next state, and we can use k-map to simplify, and we obtain n0 as s1 XOR s0 and n1 as s0 plus 0. So next, so in the design we will create an FSM and we will do the encoding bit, then the state table, and then the combination circuit. So if you want to have a counter from say 0 to 9, BCD counter. So this is the A is this with this is FSM, and this is the encoding. So we have from 0 to 1, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 6, 6 to 7, 78, and 8 to 9. So we obtain the state table, and then we use the say k-map to simplify it. So this is the expression for n3, and this all this ones we have to consider. So we can use the k-map to simplify this. Like just I will show for say n0. So n0 is like s3, s2, s1, s0. So 1, 0, 1, 0, 1, 0. This and this forms a group of 8. So this one is sorry for N0. N0 is equivalent to um, S0 complement. Similarly, uh, we can simplify the expression from N0, N1, N3, N2, N3. Okay, so going to the next topic, like using other flip-flops in the counter, so we take the benefit of the dual input reset because here JK we have two inputs. So counters can be implemented using the smaller combination circuit. Uh, so now we need to use the excitation table because before D flip-flop output is the like what is the next state will be the output of D flip-flop. But here we need the excitation table and this topic I made out still here. State table. Okay, so how to write this table? So if the present state is 0, the next state is 1. So the present state is 0, the next state is 1. If the next state that because we want to simplify using the KMAP, so it is good to write the present state in the order and see the state diagram FSM and then fill what is the next state. It is 0, it is 1, 1, 2. So in this way is we start filling it. So 1, for 1 it's 2, for 2 it is 3, for 3 it is 4, for 4 it is 5, 6, 7, 8, 9, 10. So that it will be easy to fill the KMR. If you write here 1, 2, for 0 it is 1, for 2 it is 3. But when writing the KMR for simplification, you have to take care for exactly for 2 value. It is good that you fill in the order for present state and accordingly you fill the next state. Is it clear? State table using KMAP. If this is the state table given, for KMAP, say N0, we are simplifying this one. So this is in order, right? Now, for the 0, this bit position, it is 1. Next, it is 0. So here 0. Say I will just do one more KMAP. So, then say we are filling for N1, S3, S2, S1, S0. 0, 0, So this is the schema. Now there for this n1. So for the 0th bit it is 0, then it is 1, and it is 1 for 3. So I mean 2. For 3 it is 1. 3 it is 0, and then 4 it is 0, 1, 1, 0, 0, 0, and this will be not captured. So we can form a group of 2 only. No, here we can form a group of 2. And here 2. So what will be n1? S1 S0 complement plus S3 complement S1 complement S0. Is it clear now? This is the simplification. So this we can use it for write the combination part of the circuit of the design. So now we will see for the other flip-flops, if you want to excitation table. Excitation table means it is with respect uh, present state output and next state output. For that, what will be the input we want to give? So Q is the output previous, and Q plus is the present output. For that, what will be the input? Like for if it is T flip-flop, what will be the T flip-flop value? So we know that if it is 1, it will perform the complement. If it is 0, it will be the same. With this, we have all the 4 combinations of Q plus. So this is same and this is same. That means T is 0, and this place it is complement, so T is 1. So the excitation table for T flip-flop is this, and we can draw it from this characteristic equation, like, or we can also have a state diagram and then the excitation table. Any doubts in excitation table? So again for the D flip-flop, whatever is this value will be the DN. That is the excitation table. And for JK flip-flop, get 0, 0. Like present state is 0, the next state is 0. JK, if it is same, so 0, 0 memory state or reset state 0, 1. So this means 0x. So next 0 to 1, it is like a toggle or set. So JK can be toggle 1, 1 or set 1, 0. This is 1x. Next 1 to 0 is again a toggle or reset. So it is x1. 1 to 1, it is again same state. 0 0 or set 1 0. So it is x 0. So this way we can write the excitation for table for JK flip, or this is the state diagram for the JK flip, and we can map it to the excitation table. Next is the excitation table is different from the characteristic table. So characteristic, what will be the input of flip flop? Get like we have if we have an input 0 0, then what will be the next state that is given by the characteristic table. And if we have a present state which goes to the next state, then what will be the input needed to be applied to that flip flop we obtain from the characteristics table. So this is like present state, next state. What will be the input combination we obtain from the excitation table? What will be the input to get a next state? We will get into characteristic table. So this is the two tables. I hope the terminology is clear: characteristic table and the excitation table. Okay. So now we will assign the counters with the flip flops. So we have a flip flop, then we need some set of combination logic or the logic network. So this is the synchronous counter using D flip flop. So this is the counter. Now this is the present state. Next state, what will be the D input? It will be same as this one. Because excitation table is this B and then D. We got this. Now these are the flip flop present state and these are the flip flop inputs. So what will be the equation for D1, D2, D3? So again, this we will use the K-map for simplification. And here we have written 0, 3, 5, 6, 1. When filling the K-map, this should be considered taken care. So Q1, Q2, Q3. This is 0, 1, 2, 3, 4, 6, 7. Say I'm doing it for T1. For 0 it is 0. For 1 it is 0. 2 it is 0. 3 it is 1. For 4 don't get 5 0. 7 don't get yes. And so D1 is equivalent to Q2 Q3 plus Q1 Q2. So in this way, if this present state is not in the order, then the filling of came up, you should take care this way. Is it clear? The next counter implementation. Now we got the equations, so we can directly implement them. This combination part and the D flip flop, because we know what we have. Next, if we have a T flip flop, then this part will change. This we should use the excitation table to fill this. Like it is 0, 0, this T value will be 0. This is 0, 1, that means complement T will be 1. Okay. Now for the present state and the flip flop inputs, what will be the equation we have to use the KMF for simplify. Say this is 0. I just show for y. Q1, Q2, Q3. So say T1. So for 0 it is 0. For 2 it is 0. For 3 it is 1. For 6 it is 0. For 5 1. 1 0. Yes, therefore. So T1 is given as Q1, Q3. Sorry. This is the Q2, Q3. And this one, Q1, Q3. Yes, you can see this. Next, we have obtained the combinational part. So we can use that for the input of the T flip. Next, if we want to use RS flip flop, again, we have load case also. Based on this, we will have more number of inputs. So we have to fill, say for example, 0, 0. It is 0x. So R1, S1 is 0x. So in this way, this we will fill this table using this excitation table of RS flip flop, and again present state flip flop inputs. We update something. 6 is 1. T1 we are solving. 6 is 1 and 3 is 1. So 3 and 6. And this group will should be Q1 and this 2 as Q. Yeah, this is correct. Here we are solving for T1. This is 1, 3 and 5 is 1. This is 3, this is 5. I think this is also right. If I form a like this, then what will be T1? Q2, Q3 will remain same, plus Q1 and Q2 complement. That's the equation given here. It can be the solution. QMAP, like we have known case and also the KMAP. It's not like always be giving the unique solution that you have to be seen. So it's a Q3, Q2, and Q2. Now again for we will have equations for like for this we will need 1 came up for this 2, 3, 4, 5, and 6. So total we need 6. We have to draw 6 came up and simplify and get 6 equations. These are the equations. Let's say for example, in this they have shown the simplification for S1, which is this one. So 0, 3, 6, 5, 1. So it is 1 at 5. Sure for what it is. 1 for 3. I think it is filled for R1. It's just that means for 0 and 2 it is 0, and for 1 again 0. For 3 it is 1. For 6 and 5 it is don't care, so that's not 1. We can form a group of 3. So R1 we obtain uh, 1. So 2, 1, 2, 3. I think this should be S1 unnecessary. So this is S1. Next. So this is the computation again the combination of we have obtained for this, and we need the we have written for the SR. Next, if you want to use JK flip flop, and now you can observe that the combinational circuit is like 4 AND gates, and here we needed more combinational circuit compared to this when we are using a SR flip flop or a JK flip flop. For JK flip flop, again, same we have the persistent table and the flip flop with the JK inputs, and each J and K we have to use the gamma for simplification. Next, we have seen that D flip flop requires more logic compared to the JK flip flop, and same as FSM controller. And T flip flop still require more logic compared to the JK flip flop, and RS require more logic as compared to the JK flip flop. So from this, we observe JK flip flop as require little lesser number of combinational logic. And why JK require less? Because it has more mode cases. Here and SR has don't care, whereas this doesn't have, so it requires more logic. Now, what is million mode FSM? And we'll see the parity encoder. So First taking a melee example by example, we can define the output for every this transition. Okay? For every state we have an output, but here the output depends for melee output depends on the input. So based on the transition, like with the input, it is transitioning from this, we have a particular. So if we have a circuit, and for more, this is the output for the state, and this is the output. For transitions, based on inputs, does the transition, but output only depends on the state, not on the input. So if we have more FSM, this is the output. Output depends on the state, but state depends on the input as well as the previous state. And similarly, if we have a melee, the output depends on the input because output is taken from here, which depends on the previous state plus the input. So melee machines have lesser number of states, but output will have a transition if there is any transition in the input. So any glitches in the input can be seen at the output. And more machines are safer because output changes at the clock edge. And so in melee machine, input change can cause output change as soon as the logic is done. So it's a problem when two machines are interconnected. So like here, input change does not affect the output, but it depends on the clock for more. So it is safer place. So melee machine will react faster to the inputs. More machine require more logic, so be necessary for decoding. But into the output there may be more delays after the blockage. Output x is equal to 1 whenever it receives a multiple of something. So let's just come. So if we have a more machine and we are designing, say, something like one output is 1 whenever we receive 3 times our 1. So we have a state and we have output 1 here, 1, 2, 3. 3 times 1, it is 1. But in a melee machine, we need to write the output in the transition. So for 0 transition and for the 3-1 transition, the output is 1. And not depending on the state. That's why we didn't write inside, but we are writing the transition. So here if we see only 3 states are needed. This is another example for a melee machine. So output is shown here with this present state, and this input, the output is true. So up to true if last 2 bits are same. So here we need 1, 2, 3, 4, 4 states plus 1 initial state. But here we needed 2 plus 1. So 3 states only. But it is 5 states. So this way, like more machine needs 5 more number of states compared to the melee machine. Okay, so next topic will be to the optimizations. So we say two states are equivalent if S1 and S2 are equivalent. If for every input sequence applied to the machine goes to the next state and out. And two states are said to be distinguishable states if and only if there exists at least one finite input sequence for which different outputs are produced. For optimization, we have three methods: row matching, partitioning, and implication chart. So we will see all these three methods. Row matching method. So sequence. Okay, so we will have say this is the state diagram and the state table. So now we want to minimize this. So we first step for minimization is for particular present state. If this next state is same and output is same, that means these two are equivalent. So S4 is equivalent to S6. Next, this two state can be merged. And say we can merge this to S4 dash. Next, okay, so we have replaced also with both S4 and S6 with S4 dash. Now, these are having same state, so S3 is equivalent to S5. Because this is also same. So S3 is equivalent to S5. This is equivalent to S3 dash, S3 dash. So these two are also equivalent. That means S1 is equivalent to S2. That means this I can replace with S1 dash and this with S1 dash. S1 dash. That means it is equivalent to S0. So S1, S2 and equivalent to total from here. I just can think. S4 and S6 are equal. S4 and S6 are equal, so this we said S4 dash. The next S3 is equivalent to S5 is equivalent to S3 dash. And then, okay, I think S0 is different. Yeah, this is S1 but different. So, yeah. S0 is different. S0 remains different. And S1, S2 are same. So we have total 4 states. Yeah. So next, this is our minimized episode. We can see that these two episodes are equivalent, but the implementation will be different. So the problem with this row matching is that it does not always yield the most reduced table. So next method is the partitioning method. This is the procedure, the steps you will see when solving one example. Initial partition, we have to see the output and based on the output we will partition. So this and this. That means A, B, and D are separate. C, F, and G are in different set. A, B, D, C, D, F, G. And now next partition we have to do. Okay. So let's consider this. So if it is ABD and the input is 0, so what will be the next state? For the A, it is B. The input is 0, so B. For B, it is D. For B, it is B. If it is 0. And if it is 1, C, F, and so this way we will get this. Now, C, F, G are in the same set. P and D are in the set. All fine till here. And for C, E, F, G, for two different inputs, we will obtain this as the next state. Now, we see E, C, and G are in the set, but D is not in this set. For D, the corresponding value is F. So this means F is from a different set. F is a unique set. The other sets we keep same. Again, we will check for this and for this. So for ABD, 0 and 1 state, and again CEG, 0 and 1. So for 1, again we have an F. F is not from this set. That means F we got it because of this B. B is a separate unique state. And all F seems it is a separate set. Same E, C, G are also from the same set. So it is fine. Now again we have to, this we have checked, this and this. Only this is remaining. So this we have to check. So for A and D, 0 gives B, D, which is S in the same set, and 1 gives CG, it is also set. So we get this as the reducer. So we need to say that A is equal to D, C, E, G are equivalent, F is are different, and B is different. So we need. So we need 4 different states. This is the minimized state. And the minimized FSM state value. So now if you want to minimize for this, again the state table. And from this, we have to separate based on the output. So this is a different output and the other are from different. So we have again for each thing what will be the next step. So for example, you consider this 0 and 1. Here S2 and S0 are different. This is from different sets. So this 2 should be a different one. Then further we have to check S1, S0 and this. So we're checking for this. S2 is different and S2 comes from S0, so S0 is different. And S0, S1, again, so for S1, it is S0 is different. So next S3, S5. So again, this and they are from same set. This is also same. That means no further partitioning is possible. So this is the reduced minimized expression and the minimized state table and the minimized expression. So this too has same output, but next state is different. If we are using the row partitioning, row method, not the partitioning one, row matching method. So these two are not same, so that's why we cannot merge in the row matching method. But if we are using the partitioning method, we will take S0, S2. Now for the 0 and 1, what is the next step? S0, S2, S1. So this is in the same state, this is in the same. So we can merge S0, S2 and S. Okay, so any doubts still here? Both the optimization methods, row matching and partitioning method. Do you have any doubts? Yes, partitioning method. Yes. Let's take this example. First step is to partition based on the output. So this and this are having same and different compared to the other states. So S4 and S6 one group and other states in another group. So this is first step. Next, what will be the next state if the input is 2 and the input is 1? Same will follows. This we have to check. So now if we consider this and then perform that operation. So for S0, it is S1. For S3, it is S0. No, sorry, S1. We have to check for S1, it is S3. S2, it is S5. And S3 and S5, it is S8. So in this way, we will obtain this next state. What is the state value? State if the input is 0 and if the input is 1. Now S1, S3, S5 and S0 belong to this set. It is in the same set. But these two elements belong to this set and the other element belong to this set. That means this two should be in separate set and this should be in separate set. Means the present state which gave this two set is S1 and S2 should be separate set and the present state which gave this as the next set are S0, S3 and S5 should be in the separate set. So we got two more set. This is that. Again, now we have to see what will be the next set for 0. So say for this, we do 0 and 1. Again, this and this are in the separate. That means S0 is separate. We got S0 separate, 3 and 5 separate. Now we are left with this, this, and this. So 1, 2, 3, 5, and 4, 6. So again, if you see, they are in the same set. So that means we have reached the, like, further partitioning is not possible. So this is the reduced form. That means these are equivalent to this. Sorry, not this. These are equivalent. These are equivalent. These are equivalent. This is S1, S2, S3, S5, S4, S6, and S0. This is the minimize. Now we can reduce this to this state. That means from the state table, we can merge all this rows, and this will be the minimized episode. Clear? So next, so the next method for the state reduction, we will see the implication chart method. This is the state diagram, the FSM table, state table. Now in implication chart, if we have a chart, say S0 to S6, then there will be, say, this, which is equivalent already same as S1, S4 or S1, S4. So that means we can have from S1 till S5. This portion alone, if we use, it will be sufficient. So that we take it, and this is the called as implication chart. Now this is the procedure. You will start solving. Yeah. So now from this, S4 and S6 are having one as the output. So S4 and S6, we don't know if they may be equivalent or not. So we are not given cross mark. But S4 is not equivalent to other states. So because outputs are different, so we have marked with cross. And S5 is not equivalent to S4. S5 and S4 are different. So next step. Will S1 be equivalent to S0? Yes, if S1 is equivalent to S3 and S2 is equivalent to S4, then there are chances that S1 is equivalent to S0. So in the similar way, we fill for all the equivalents for the states. Now we observe that this is same. So this is always possible. This is possible. So in this way, we will start. So first, it is given that S1 should be S3. It's S2 and S4. This cross. So this is not possible. So in this way, we start eliminating one by one. So next, this one. S1 and S5. This is already a cross, so this is not possible. Next, S3 and S5. S2 and S5. If S3 and S5 are same, this means S2 S4 and S6 S4, yeah, S4 and S6. This is already equivalent. S3 and S5 are also equivalent. This is equivalent, this is equivalent. So that means this is equivalent. Next, this one, 3 and 0. 3, it's not equivalent. That means this is also not equivalent. And 5 and 0, 5, 0, and 6 and 0, 6, 0. This is not, this is. So in this way, we will mark cross and eliminate. These are not possible. So S1 and S0 not possible. So this is already S5 and S0. So this will be obtained. This 3 are equivalent. So this equivalent. From this we obtain the reduced state table and the minimized FSM. So any doubts here? In this method of using implication chart to minimize the FSM. Implication chart method, elimination process. So first elimination is we see the output. If they are different, we eliminate those because even though this two, if it becomes same also, sorry, not this two. For example, this is same. So if S4 and S5 become same also, because outputs are different, those two states can never be same equally. So we can eliminate safely wherever the output is different. That is S4 is not equal to any state except S6. So except X6. So this we eliminate. This should be X6. Oh, sorry. And for S6, it is not equivalent to any other state except S4. So this we leave it blank and other states are removed. S5 and S4 also it is not equivalent. So cross. First step, based on output, we have eliminated. Next step, we start filling each of this empty because outputs are same. So by any chance, if S1 is equivalent to S3, S2 is equivalent to S4, then S0 state can be equivalent to S1 state. So in this way, we fill for all the leftover states can be equal with this condition. Now one by one we start eliminating this condition. So S1 to be equivalent to S0. We want S1 to be equivalent to S3 and S2 to be equivalent to S4. S4 cannot be equivalent to any other state except S6. So this is eliminated. So S2 and 4 are equivalent, 3 and 5. So this is equivalent and this is equivalent. So this is equivalent. Keep it. This is the merge state. And again S6 with S2 is also not possible. S4 with this is not possible. S4 with S0 is not possible. Now S1 and S0 we eliminated here. So this is also not possible. Again S1 S0 is eliminated. 4 with any state is not possible. 6 with any state is not possible. So we are left with these three states, 1, 2, and 3. These are the reduced states. So after similarly reducing, yeah, we get this three state as equivalent state. So in the state table, one of the state is enough. The other state we can get. Is it clear now? Okay, so next. This is the reduced state table and the reduced. Next, we will see the state encoding and the assignment. So we have to assign a unique binary value to each of the state so that we can implement in the FSM. So if this is a state, we need to assign it before we are giving like this some binary equivalent. So if we have say 4 state, then total we are using all the say bits. So total 4 factorial combination. So the number of states are 4, then the 4 factorial combination. So what are the combination possible? This can be one combination 0, 1, 2, 3 or 0, 1, 3, 2. So like this, there can be 4 factorial different combinations. So which one we can follow? And similarly, since we don't care about the absolute flip-flop value, say, suppose we have 6 states for a model 6 counter. And if we have a 3-bit encoder, that means 6 states can be represented in a combination of 3 bits. So it is 6. First of all, 2 to the power 3, we will get 8 bits. So out of 8 bits, we want only 6 bits to be encoded. This can be done 8 with the combination of 6 and the formula which is 8 factorial, 6 factorial into 6. 8 minus 6, It will be like 7 into 8 divided by 2. So exploring this all this combination for the encoding is not possible. So there are few methods like we can have an encoding tree, which is some form of encoding, or we can use a gray code or a binary code. So gray, binary and gray can be used the minimum number of bits for the state register, or if we can want minimum number of transitions between the two codes, then we can use gray or the Johnson counter. So two adjacent codes differ by only 1 bit. So we want reduce simultaneous switching. So this will reduce the glitches and the cluster. So one hot encoding means if we have 3 flip-flops, then we need 3 bit. At a time, only 1 bit will be 1. And so how to assign the state? If it is binary, 2 to the power n state for n flip-flop, or 1 hot n states for n flip-flop. And gray also 2 to the power n for n states for n flip-flop. So this is some example where this is given 0, this is 0, this gives 1, this gives 1. So some FSM from this example. This is the state diagram and state table. Now we should go for the encoding. So if we use the binary, so 0, 1, 2, 3, with this is the combinational logic we obtain. Whereas if we go for gray, we can see there is little reduction in combination. So gray code encoding. Next, say 1 hot coding. So we need 3 bits for 3 states. And at a time, only 1 bit is 1. So if we use binary, this is the encoding. If we have 7 states, so 7 states, so 1 hot will have 7 bit. And sorry, 8 states, 0 to 7, 8 states. So 1, 2, 3, 4, 5, 6, 7, 8. 8 bits. And gray code again 3 bits. So this will be, and Johnson and gray differ by each previous and this will differ by only 1 bit. And we saw that this much exploration is difficult. So 1 hot coding. So we want that minimum bit change in coding like yes. So if you have a Johnson counter, say 4 bit. So each time we are like getting this. Next, this. The next counter output will be this. This will be 0, 0, 0, 1, 1, 0, 0, 0, 1. Again 0, 0, it will start. So this is the Johnson code obtained from the Johnson code. And writing here, I think they have written in this direction. Okay, I just want to draw the circuit because Johnson counter, we have seen, if we consider 4-bit, D flip-flop, Q, D, Q, D, Q. This bit will complement and then give input here. And we'll have the same clock. This is called the Johnson counter. And here we observe that every, like this and this, there is only one bit which is changing. So Hamming distance is 1. Again 1. So here also 1. Every next successive code, we will have just one bit difference. Any other doubts? So next, we just come to directly to the rules and then examples. So the rule 1 states that from S1 and S2, we are going to the same state. So that means S1 and S2 are like adjacent. And according to rule 2, S2 with the 0 input goes to this and 1 input goes to this. That means S1 and S2, they are the next state of the S0. So they are adjacent. And rule 3 is a like common output. This output is also 0. This is also 0. This also is 1. This also 1. Like it's coming output 1. Next output 1. So they are adjacent. So 2, 3 are adjacent. Again here 0, 1 are adjacent. So now if we apply this 3 rules to simplify this state diagram, according to rule 1, from S1 and S2 is going to the same state, S3. So that means these two are adjacent. So we want Hamming distance 1. Next, rule 2. S1 and S2. So this state S0 is going to this. So this again, this two should be adjacent. According to rule 3, based on the output. Say 0, 1 not possible, 0, 0. Like this is 1, this is 1. So S2 and S3 should be adjacent with output 1. And this is 0. This is again 0. That means S0 and S1 should be adjacent. So this 2 we wanted to be adjacent. This 2 we wanted to be adjacent. And this 2 to be adjacent. That means we want having distance 1, like minimum number of transition between these states. So we will choose encoding in that way. And we will solve some few questions. Then I think we will get back here. Okay. Question 1. Let us assume we want to design a 3-bit. Okay. Any doubts till there? Um, so that now let's solve this question. So let us assume we want to design a 3-bit counter using the flip-flop based on the following state diagram. Calculate the function inputs D1, D2, D3 for the D in flip-flop from the present state Q3, Q2, Q1 for of the counter. So what will be the equations? Yeah. So let's solve this. The next state will be the output. So you can directly write the present state and next state alone. Present state, next state. If it is 0, it goes to 1, 1, 2, 3, 0, 0, 5, 6. So this the table is here. We have drawn from the state uh, diagram. So we will encode it directly. So 7, so 3 bits should be fine. We are using the binary encoding. So this will be so I think here Verilog came up because this gives say we have Q1 like D inputs D3, D2, D1. It is Q3. 3, or if you take it like this, D1, D2, D3, then this is D1 equivalent to Q1, Q2 complement, Q3 complement. And this is D2 equivalent to Q1 complement to Q3 complement. D3, D3 will be from this. So D3 is equal to Q1 complement, Q2 complement, Q3. Like this, including will be correct. This Q3, Q2, Q1, I must be told. So now D3 is equal to Q3, Q2 complement Q1 complement. D2 is equal to Q3 complement Q2 Q1 complement. D1 is equal to Q3 complement. And this is the procedure to solve it. Going to the next question. Which of the following statement is false? In mode machine, output depends on the present state as well as the present input. Mode only depends on the present state and not on the present input. So this is false. Next, Mealy machine. More number of states compared to the Moore machine, which we have seen, it is not more, it consists of lesser states. So this is also. The answer is both S1 and S2. Just the method. Based on this Q1, Q2, P3, how we are taking, and D1, D2, D3, how we are taking, equations may change. Next question, thought, which of the following statement is true for William machine sequence director? Which deduct sequence from a state state. So, Mealy, we have the same state as the number of the bits because sequence director, say third sequence, we have vectored the sequence. Directly in that entry, we can view the output. So, Mealy leaves the same number of state. Next. What will be the final partition for the state minimization using the partitioning method for the following state diagram? So again, we need the table. Present state, next state, one, x is equal to 0, output, Present state 1, 2, 3, 4, and 5. So based on this, from the diagram, we have to fill this table. So it will be 5, 3, 1, 1. Again 5, 3, output will be 1, 1. 1, 2, output will be 1, 0. 5, 4, 1, 0. 1, 4, 0. So based on the output, we will have 3 different groups. Now we have to check for 1 and 2. 3 and 4 also. So 3, 4. What will be the next step? Based on 0 and 1. 3 will go to 1 and 4 will go to 5. This will be 2, 4. So 1 and 5 are in different set. That means if I want to separate like 5 is because of 1. So again we have to separate 3 and 4 separately and 5. And 1. So 1 and 2 goes to 5, 3, 0, 1, 5. So these are in the same set. I have made this same in 5, 5. For 0 it is 3, 1 it is 5. So for 0, 1 it goes to 5 and 0 it goes to 3. That means these are equivalent. So what is equivalent? 1 and 2. 3 is different, 4 is different, 5 is different. Okay, next question. Suppose we want to design a synchronous model of 5 counter model using more FSM with 5 state. Calculate the number of possible encoding if we use 3 bit to encode the 5 state. 3 bit, so total 2 to the power 3 combinations, which is 8 combinations. So out of 8, any 5 combinations? This will be 8 factorial divided by 3 factorial into 5 factorial, which is nothing but 5, 6, so 6, 7, and 8 divided by 2 into 3, which is 1. Fine, going to the next question. Consider the following state encoded FSM. What will be the total Hamming distance for the state encoding? So this to this 3-bit difference. Again 1 here 2 for this 2 for this 2. So answer is 3 plus 1 plus 2 plus 2 plus 1. 5, 6, 7, 8, 9, 10. So total. Next question. Suppose we want to design a counter using D flip-flop such that it counts this sequence. So the expression for the given D to D channel. Again, present state. What will be the next step? So D flip-flop, so directly it will be that. 5, just it is 2, which is 0, 1, 0, 0, 3, 6. This is not given in the and 1, 6 means 5. Now you have to use the KMRF to simplify for every bit. D1, D2, D3. Q1, Q2, Q3. This one I am doing 0, 0, 0, 1, X, 0, 1. And this is 1 plus 7. This means B1 is equivalent to Q2, Q3 plus Q1. I think by simplifying this, we will get expression for D1, D2, and D3. Present state here it is Q3, Q2, Q1. This is how they have considered. In 1, 0, 1, 1, X, 0, 0, X. Like this. D2 is equivalent to Q1 bar Q2 plus Q2 bar. And one more. I think I can draw one more state given here. One, 0, X, 1, 1, X. This and a group of 4. So we get Q1 plus Q2, Q3. Then this is the method to solve this. This next question. Based on the output and if it is same state. This is having same state, same output. And this one. This is having 3 and 4, 0. 3 and 4, 0. This we will just merge it. S0 is same, S1, S2, 0. S1 dash, S3, S4, 0. Like we want this and this. So S4 is equivalent to S6, S1 is equivalent to S5. This will be called as star 0. And S2, S5, S6, 0. S3, S3, S4, star 0. The next S4 is already written. No, S4 we have written. S5, S5 is yeah, S1 star. And S6, S6 is again S4 star, S4 star, and S6 is S4 star. S3 has an output of 1, other 0. From this again, can we simplify it? S1, S4, one S, this one, S1, S4, have S0. Now let's write it again. Present state, state, so equal to 0. Okay. S0, same. This one also same. And you become star. S3, S4 star, 0. S2 star now. S2 is equivalent to S4. S2 is equivalent to S4 star. So again, say let's skip this step. Or let's just keep it as S4 stars. S4 star, S1 star, S4 star. So again, this should be S4 star. Below S3, S4 star, 1, S1 star, S4. This will be one separate set. This will be one separate set. Like, and this, I change the color. This can be merged with this and can be merged with this. S0 is equivalent to S4 star is equivalent to S. So this we have total 3 states. Okay. So any doubts still here? Question maybe the definitions. Let's just do this way. And even This one is giving V1 equation. V1 is this one we represent V1, V2, V3. This equation, so I'll just write it again. This represents V3 and this is obtained for 0, 1, V. So this is Q3 complement Q1 complement. It's 4, right? Yeah. Getting the this way of taking is correct. D3, D2, D1, MS beta SP, Q3, Q2, Q1, MS beta SP. So for this we need this way one. That means D2 is equivalent to Q3 complement to complement Q1. Yes. And D1 is equivalent to this is obtained from 0, 0, 0. That means Q3 complement Q4 complement Q1. Okay. So this is the text. Okay, so any doubts? First, this we get based on the output because these two are different, this is different, and this is different. Now, this and this, we have to see what is the next state based on 1 and 0. So, if 0 is the input, what will we get here the next state? For 3, it is 1. So, it is 1, 5. And for 1, 2, 4. 2, 4. Now, 2 and 4 are in the same set? No. So this we will substitute. That is 3 and 4 are substituted. So we get 3 and 4 substituted. Now for this 1 and 2, it's 5, 5, 3, 3. So they are same, so they are equivalent. Like they will come from the same set 5, 4, power 3. So this is one set. So the total reduced is 1 to 3 separate, 4 and 5 separate. Is it clear? Table is from this diagram. From 1, it is going to 5 if x is 1 and output is 1. And from 1, it is going to 3 when input is 0 and output is 1. In this way. So if I take state 2, input is this, so it goes to 5. I will fill here 5. And output is 1, so I will fill 1 here. And from here, if I give 0, it goes to 3. So I will fill 3 here, and output is 1. So in this way, we will. Yes. Any other doubts? So if no other doubts, then we can end today's session. So I will end the today's session. Thank you so much for joining.